Good day. The first part of study unit 2 focus on the basic probability concepts in sections 1.1 and 1.2. If you look at the outcomes in the study guide, you should be able to understand and apply all these basic concepts to practical problems. There are different terms for probability that we use every day that you might not have realized. For example, what is the odds that the Proteas will win a World Cup final? Well, not very good if you look at their track record. Or what is the possibility of rain tomorrow? Or what is the likelihood that a new method will work? Or what is the chance that the investment will be profitable? There are three different interpretations of probability. The first is the classic interpretation, where all outcomes have equal probability. For example, if you have 49 lotto balls in total, every ball has a chance of 1/49 of being drawn. If you do not replace that lotto ball, all the other balls will have a chance of 1/48 of being drawn on the second draw, etc. Or if you look at the toss of a coin, the probability of heads is 0.5 and the probability of tails will also be 0.5. Then subjective probability, we work with educated guesses or the use of models to estimate probability. For example, a doctor that estimates the survival rate of a patient after surgery, or a climatologist that uses a model to predict weather conditions for the next day, the chance that it will rain, for instance. And then thirdly, we have the frequency interpretation, where probability is based on relative frequencies. For example, in market conditions, let's say that you want to determine how many times in the previous 24 months did a certain investment show a positive interest rate. Then you would physically count the number of times it was positive, and you would divide by the total number of months, and that will give you the relative frequency. Probability theory provides the foundation for statistical inference, where we have sample data and we use that to draw conclusions about the whole population. And you experienced a bit of this in ANOVA, for instance, when you did the hypothesis test. So we had a probability value, which was the p-value, and you wanted to make a conclusion on the difference between the different population means based on sample data. There's a few definitions that you should take note of. First of all, experiment is the process that generates outcomes, but the outcomes can't be predicted. So even if you do the experiment in exactly the same way, you won't necessarily get the same results each time. For example, if you toss a coin, you don't know beforehand whether you will get a head or a tail. Then a sample space is also known as the outcome space, and this is a set of all the possible outcomes or elements of an experiment, and the sample space is denoted by this omega symbol. For example, let's say we have these 4 experiments, so let's quickly list the outcomes for the experiments. So tossing a coin, there's 2 possible outcomes in my sample space. You can get a heads or a tail. If a telemarketer conducts a sales call, he can either make a purchase or there can be no purchase. Or if you roll a die, the possible outcomes in your sample space is a 1, 2, 3, 4, 5 or 6. Or if someone plays a soccer game, then the team can win, lose or tie the game. Then we can also look at multi-step experiments, and those are experiments that are repeated more than once. For example, let's say that you toss a coin twice. Then the outcomes in the sample space is going to be heads, 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 tails, tails, heads, or tails, tails. So with 2 possible experiments, it's easy to list the outcomes. But if you have more than 2 multi-step experiments, then it becomes a bit more difficult. So there's a useful tool that helps us graphically represent the outcomes, and that's called the tree diagram. So let's look at an example. In example A on page 2 of RISE, they give you the following scenario. Driving to work, a commuter passes through a sequence of 3 intersections with traffic lights. At each light, she either stops, which is denoted by S, or she continues, which is denoted by C, and I want you to list the outcomes for the sample space. Now, for the first light, there's two possible options. She can either continue or stop. Then at the second traffic light, there will also be two possible options, continuing or stopping, for each of those outcomes at the first traffic light. And then for the third light, we will have two possible outcomes each time again. So then to list the outcomes of this multi-step experiment, we just read off the outcomes for the branches from top to bottom. So you will have 8 outcomes in total as listed here in your sample space. An event is a subset of a sample space. It's indicated by this symbol, and events are represented by uppercase letters. So an event can contain all the elements or outcomes of the sample space or some of the elements of the sample space. For example, let's say that my sample space represents all the alphabet letters. Then event A can be defined as the vowels in the alphabet, for instance. Then it will only contain 5 of the 26 alphabet letters. Then we can graphically represent sample spaces and events with Venn diagrams. So in a Venn diagram, the square will indicate the sample space and the circles will indicate the events. For example, in figure 1.1, that will be an event A that is within the sample space. So event A is a subset of the sample space. Okay, let's look at a practical example. In example 1.4, they tell you, suppose you roll a die. Let A be the event that an even number is obtained. So rolling the die, the outcomes on the die can either be 1, 2, 3, 4, 5 or 6. If we are looking for the even numbers, then the outcomes in event A will be 2, 4 or 6. So that means that A will be a subset of my sample space. In example 1.5, they tell you, Lizelle and Peter can do 3 different dances, a waltz, a tango and a samba. For the competition, they must decide in which order they will do these 3 dances. So we can let W denote a waltz, T tango and S samba. Now you need to be careful when you draw your tree diagram, because for the first dance there will be 3 possible choices. They can do the waltz, the tango or the samba. But for the second dance there will only be 2 possible outcomes each time, because they can't repeat the first dance. So for the second dance, for instance, if I did the waltz first, they will do the tango or the samba second, etc. And then for the third dance, there will only be 1 outcome each time. So if they did the waltz first, the tango second, then they will do the samba third, etc. So our sample space will contain these 6 possible outcomes. Then in question B, they defined event A as the event that they do the waltz first, and let B be the event that they do the samba before the tango. So if we look at the outcomes in event A, we will look at all the outcomes where W was in the first position, and then for B, where S was before T. So it will consist of these 3 outcomes. So S can either be directly before T, like in the first 2 outcomes, or S can be in the first position and T in the third position. So that that outcome will also be included. Then for question C, they asked you, describe the words the event C given by these outcomes. So in all of those cases, T was not first, so C will be the event that the tango was not done first. Okay, there's another example on page 2 in RICE that you can work through yourself. So there they wanted to let A denote the event that the commuter stops at the first light. And the outcomes are listed in your notes there. Then the next concept is the union. So the union of two events A and B is the event that either event A occurs or event B occurs or both occur at the same time. And the notation that we use to express unions is this notation, A or B. If you look at the Venn diagram, this part of event A will indicate that only event A occurs. This part will indicate that only B occurs, and where they overlap, that will be the outcomes that they have in common, so both A and B occur in that space. Then continuing from 1.5, we identified these events, and now they ask you to determine the union of A or B. Okay, so we list all the outcomes in A and then all the outcomes in B. You will see these are the two outcomes in A then, these are the outcomes in B, and WST occurred in both A and B, but you won't list that twice because that's one of the outcomes that they have in common. Then if we look at the union of B or C, then we will list the outcomes of B and then also the outcomes of C. And again, they had these outcomes and those two outcomes in common, so you only list them once. And there's another example on page 3 of Rice that you can work through on your own time. For the intersection of two events A and B, we look at the event that both A and B occur at the same time, and the notation that we use to express intersections is this notation A and B. And if you look at the Venn diagram, we will only look at the outcomes that occur both in events A and B at the same time, so where they overlap. So continuing from example 1.5, to get the intersection of events A and B, for instance, there was only one outcome that they had in common. It was WST. So the intersection of A and B will consist of only that one outcome. If we look at the intersection of B and C, they had this outcome in common, also STW and SWT. So the intersection of events B and C will consist of these three outcomes. And again, there is another example on page 3 of Rice that you can work through. The complement of an event A is the event that A will not take place. So here we look at all the elements or the outcomes that are still in the sample space but not included in event A. And there's different notations for indicating that. A superscript C, A prime or A bar. The one that is used in the notes is A superscript C. So if you look at your Venn diagram, if we have an event A in our sample space, then A's complement will lie here. So it consists of all the elements that are still in my sample space but not in event A. For example, continuing from example 1.5, this was A and C. So A consisted of these two outcomes. So from our sample space, we will take all the other four outcomes, so not including those two outcomes, and that will form A's complement. And then for C, we had these four outcomes. So the other two outcomes that were still in my sample space but not in C, that will be C's complement. And then again on page 3 of Rice, there's another example that you can study. An empty set is also called a null set, and that's a set with no elements or outcomes, and it's denoted by this symbol. For example, if you have an intersection of two events and they have no outcomes in common, then the intersection of these two events will be an empty set. So it's applicable to disjoint or mutually exclusive sets, and that means that the two events do not overlap. So they have no outcomes in common, so the intersection will be an impossible event. Here are a few examples of mutually exclusive or disjoint sets. First of all, I'm tossing a coin. Heads and tails are mutually exclusive because they can't happen at the same time. Then turning left or right. You can try, but you can't do both at the same time. Then drawing cards. If you look at kings and aces in a pack of playing cards, then aces and kings will be mutually exclusive because they have no outcomes in common, but hearts and kings won't be mutually exclusive, for instance, because you can't get a king of hearts. So that card is both part of hearts and of kings. Okay, then later on in this module, it will be really useful if you can draw Venn diagrams and indicate the different outcomes in the different sections of your Venn diagram numerically. So I included a class example for you over here. So I tell you, an IT firm has 12 programmers on staff. 6 of the programmers can program in Java, and that event is indicated by J. 4 programmers can program in Python, and that event is indicated by P. And 1 programmer can program in both Java and Python. Then in question A, I ask you to draw a Venn diagram to illustrate this situation. Okay, so first of all, you must see that you have an outcome space with 2 events, and Java and Python is going to be not mutually exclusive because there is 1 programmer that can program both in Java and in Python. Okay, so here in the overlap, there's going to be 1 programmer. Then I tell you, for Java, there's 6 programmers. So the Java only part is only going to consist of 5 programmers, since the whole of Java consists of 6 programmers, but the one that can program in both Java and Python will be part of the Java programmers. Then I tell you further on that 4 programmers can program in Python. So the 1 programmer that can program both in Java and Python will be part of your Python event. So the Python only part will consist of 3 programmers. If you add the numbers in those 3 sections, you will get 9. But I told you that there's 12 programmers in total on staff. So that means that the other 3 programmers will still be in my sample space, but it's not part of those events. So that means that those programmers can program in a different language, for instance C#, but not Java or Python. Then in question B, I ask you, how many programmers can program in Java but not in Python? So it will only consist of this part of my Venn diagram. So it will be 5 programmers. On page 4 of the notes, there's a class exercise where you can practice this concept. So they tell you, in a class of 100 pupils, 54 take maths, 69 take history, and 35 pupils take both math and history. By making use of a Venn diagram, determine the number of pupils taking maths or history in A, none of these subjects in B, and in C, history but not maths. So you can complete that exercise for me, please. Okay, let's look at the answer. So I have 100 pupils in total, and I have 2 events in my Venn diagram, maths and history, and they are not mutually exclusive because there's 35 students that take both maths and history. So in the overlap, I will have 35. I have 54 that take math. So if I subtract the 35, I'm left with 19 that takes only math. And then for history, there's 69 in total. So if I subtract the 35, I'm left with 34. So that's the pupils that take only history. If you add all those amounts, you will get 88 in total. So that means that the other 12 will not take maths or history. Then for question A, where they asked you, determine the number of pupils that take math or history. It's going to include all those three sections of my Venn diagram. So if I add 19, 35 and 34, I will get 88 pupils in total. Then none of these subjects, so it will be these pupils that are still in my sample space but not part of any of those subjects, so it will be 12 pupils. And then history but not maths, so it will be those 34 pupils in this history only part in my Venn diagram. So the answer for C is 34. You can just take note of the laws for events on page 4 of the notes. Later on, when we do the proofs, we will apply these concepts. So for the commutative law, it doesn't matter in which order you write unions or intersections, because it will lead to the same outcomes. For instance, whether you take the union of A or B or A, you will still get the same outcomes. Or for the associative law, it doesn't matter which union or intersection is done first. For example, if you take the intersection of A and B and then the intersection of C, or if you do that intersection first and then you intersect it with A, it will lead to the same outcomes. Then for the distributive law, you can also write unions and intersection in these ways, and then you'll get to the same outcomes. For example, if you take the intersection of that union and event C, or if you take the union of those two intersections, it will lead to the same outcomes. Or if you have an intersection of events A and B and then you have the union with C, or you have the intersection with those two unions, you will have the same outcomes. For law 4, the intersection of event A and an empty set will simply be an empty set, because the outcomes in A with the intersection of nothing will just be nothing, but the union of event A and an empty set will consist of all the outcomes in event A. Then for 5, the intersection of A and the sample space will consist of all the outcomes in event A. Then the intersection of A and A's complement, that will be an empty set because A and A's complement are opposites of each other, so they will have nothing in common. But the union of A or A's complement will be the outcomes in your sample space. Then for the Morgan's law, there we look at different ways of writing intersections and union of complements, and you will get to the same outcomes. For instance, if you take the intersection of A's complement and B's complement, you will get the same outcomes if you take the complement of the union of A or B, or if you take the union of A's complement or B's complement, you will get the same outcomes if you take the complement of the intersection of A and B. And then lastly, A's complement's complement is simply A because the complements will cancel each other out. You can complete these 2 exercises on your exercise sheet, please, to practice the concepts of Study Unit 2 Part 1. Thank you.